Well, good evening. Tonight we're going to do the last new material for the semester. As I recall, our final was on Monday of finals week. So tonight we're going to go over section 6.4 that we also kind of skipped over as we were going along, graphs involving exponentials and logarithms. Like I said before, we didn't want to spend a lot of time on it unnecessarily because you've already done graphing techniques that you'll see in here. But now what we're going to do is apply them to exponentials and logarithms in particular. At the time, we hadn't seen L'Hopital's rule. It came in the next section. Now that we've seen it, we can do a little better job with these exponentials and logarithms graphs. What we'll do is next, we won't meet on Wednesday due to the Thanksgiving holiday. There's no school. Then on Monday and Wednesday next week, we'll do review for the final. So sometime during the break, I'll put out a problems list to practice for the final. And then Monday and Wednesday, the last week, we'll work on those and hopefully be ready for the final on Monday, finals week. This will be the last in-person class meeting tonight. After this, again, no meeting on Wednesday. The following Monday and Wednesday will be online only, and we'll do review both times. And then the final exam the following Monday, according to the schedule of classes and your syllabus. All right, so I'll just remind you that to do these, we use symmetry. What kind of symmetry do we have? If you go back to algebra, if replacing x by minus x in y equals f of x gives the same result. In other words, f of minus x equals f of plus x, then the function is even and it is called even. And the graph is symmetric over the y-axis. Similarly, if we replace x by minus x and y by minus y, so that f of minus x equals minus f of x, then the function is odd. And the graph is symmetric to the origin. This is not a big point. I put it first, but it's not a big point. But you can look for those symmetries on some of the problems. We also use asymptotes. Just to remind you, and then again, this is from Calculus 1. But we can get horizontal and vertical asymptotes. If the limit as x approaches some number a from the left of f of x is infinity or minus infinity, or if the limit as x approaches a from the right side of f of x is infinity or minus infinity. Then x equals a is a vertical asymptote. That's the definition. The reason you can see why, right? If I approach x equals a from the left, function goes higher and higher, has limit infinity. you're approaching it like that, right? For instance, suppose I approach A from the right-hand side, here's x equals A, and maybe it goes down like this, more and more negative with limit minus infinity. Then there's an asymptote right here at x equals A. And you can approach one side infinity and the other side minus infinity or whatever. Doesn't matter what the graph does on the other side. It might not be an asymptote. This side might look like that. Or it might look like that. We still say x equals A is an asymptote. If on one side at least, it goes up to infinity or down to minus infinity. So that's asymptotes. It's nice to plot x-intercepts occur where y equals 0. So you can plug y equals 0 in and see what the x values are. That gives you the x-intercepts. And right from algebra, y-intercepts where x equals 0. If x equals 0 is the y-axis, that's the y-intercept. Let's see. We can also look at these important calculus concepts. We can seek, in our same old-fashioned calculus 1, relative extrema inflection points and I guess that's pretty much it. There are some others like cusps. These are things where you get an infinitely sharp point upwards or downwards. The river tends towards infinity on one side and minus infinity on the other. I don't think we'll do any of those here. Those are the kind of things people like to see in their graphs, especially the relative extrema, right? If that's the high the stock market had, that's where you want to sell. That's the low the drug had that hits, that's where you're most maybe in danger or something. Inflection point in business is the point of diminishing returns when you put your, I guess, revenue versus units produced, that kind of thing. So let's take a couple examples of these now for exponentials and logarithms. That's a reminder of some things you did. We also recall in this, now that we've had L'Hopital's rule, that the limit as x goes to infinity of e of any exponential function, b to the x over x to the p, with b greater than 1, is infinity, because an exponential outgrows any power of x. But if b is between 0 and 1, this goes to 0 very rapidly and forces this to 0. So exponentials grow faster than powers of x for base positive, and dive to 0 faster than powers of x can climb or descend when b is
The camera over.
1. Well, here's an example then. Suppose I wanted to sketch the graph of y equals x squared e to the minus 4x. What does this look like?
Professor, I can't see the far end of the board.
Okay, thank you. I thought I put it at the end. I guess I didn't quite make it. There we go. Suppose I want to sketch this function with a polynomial times an exponential. What do I know immediately? I could rewrite this equivalently as y equals x squared over e to the 4x. And say this goes to infinity much faster than any power of x because it's an exponential with base greater than 1. And so if the exponential climbs to infinity faster than the power of x, then with this tending to infinity faster on the bottom, this limit will be 0. Oh, I forgot to put the other asymptote on here, by the way. I guess I did the vertical ones. I think this is still on the screen here. Yeah. I forgot to finish the asymptotes. And say that if limit as x goes to infinity of f of x is 0, then you get an asymptote on the right, or is L. You get an asymptote on the right, y equals L. Or if the limit as x goes to minus infinity of f of x is L, then you get an asymptote on the left, y equals L. In either case, we say y equals L is a horizontal asymptote. We also did oblique asymptotes before. I don't think we really need that for this section, but you can get asymptotes at an angle. But I'll just remind you of that. Now, because the exponential outgrows x squared, we know it's by L'Hopital's rule. The limit, applying this theorem up here is equivalent. Limit x goes to infinity of x squared over e to the 4x, provided it exists, is the same as the limit as x goes to infinity of the derivative over the derivative, which is still in indeterminate form because it's infinity over infinity. But if we take the derivative over the derivative again, we get 2 over 16 e to the 4x. And now the bottom's going to infinity, but the top's going to 0. So L'Hopital's rule says this limit is 0. We have a horizontal asymptote, therefore y equals 0, since the limit here is this number, L equals 0. So there's our first thing we can sketch, is our asymptote. Y equals 0 is asymptotically approached on the right. On the left, it's not. If you were to take the limit as x goes to minus infinity, of x squared over e to the 4x, this thing is going to 0 faster than, and this thing is going to infinity. And if you get infinity over 0, from the right it's approaching, because these are all positive numbers. Infinity over smaller numbers has limit infinity. So we're going to have a left behavior. It's going to go up to plus infinity. And on the right, we're going to dive towards right equals 0. What's going to happen in the middle? In between, we can look for any symmetries. Well, this isn't an even or an odd function, right? If you replace x by minus x, you don't get the same function back. Replace x by minus x and y by minus y, it still doesn't work. So it's not even or odd. We don't have any vertical asymptotes because you'll notice the thing doesn't go to infinity or minus infinity anywhere in the middle. So we're down to the last part here. We'll look for relative extrema inflection points. And just relative extrema inflection points. We have to evaluate those. You can also do concavity. Maybe I should have added that to the list. I don't think this section does a whole lot with it, but you might add concavity to that list. I don't think they put it in their list in this section. So we have in order to evaluate where it's increasing and decreasing, or whether relative extrema are, we have to calculate f prime of x, which is the derivative of x squared e to the minus 4x, is by the product rule, right? It's derivative of x squared times e to the minus 4x plus x squared, derivative of e to the minus 4x is minus 4 e to the minus 4x, right? Derivative of e to the kx is k e to the kx by the chain rule, you recall? Now I've got a common factor of x e to the minus 4x, so I can say this is x, well, let's write x e to the minus 4x, and that all multiplies to minus 4x. Actually, I could have pulled out a 2, couldn't I? Let's do that. Let's call it 2x times 1 minus 2x e to the minus 4x. There's how it factors. You know what? I'm sorry. I want to do this a little differently. I should call it 2x minus 4x squared. This is the best way to do it. Sorry. So there's f prime of x. Well, let's put it back the way it was. All right. 2x, sorry about that, times 1 minus 2x. Now you observe from here that in order for the derivative to be 0 and get a critical point, right, critical points where the derivative is 0 or doesn't exist within the domain of the function. Critical points are where x equals 0, that makes this factor 0. X equals a half makes this factor 0. And this is never 0, right? Usually any number isn't 0, so there's 2 critical points. We need to check those and see if either of those gives us a relative extremum or on this function. So to check for relative extrema, now I'm going to use the other form of this, which was 2x, wait a minute. Oh, okay, yeah, minus 2x, okay. Which was 2x minus 4x squared e to the minus 4x. We can use this to calculate f double prime, right? It's the derivative of 2x minus 4x squared e to the minus 4x. These are long problems, all of them. Again, we need a product rule. Derivative of the first part is 2 minus 8x. That multiplies e to the minus 4x. And then plus first part times derivative of the second, 2x minus 4x squared times minus 4 e to the minus 4x. So there it is. F g prime plus, f prime g plus f g prime for the product rule. Now we can group all this. There's an e to the minus 4x multiplying everything. It multiplies 2 minus 8x plus minus another 8x is minus 16x. Minus 8x, and then minus plus 16x squared. There it is. There's the second derivative. Recall that the way you can check for relative extrema is you first find all the candidates by finding the critical points. Then you plug each critical point into the second derivative, and we say the second derivative test. Recall says that if the second derivative is negative at the critical point, then it's concave down and you have a relative maximum. But if the second derivative is positive, then it goes like that and you've got a relative minimum. So second derivative positive actually means minimum, second derivative negative means maximum. Maybe backwards from intuitive until you think about what it means. So apply the second derivative test at the first point and take f double prime of 0, the first critical point, and we get 2 times e to the 0. Is 2 is positive, tells you have a relative min at x equals 0. You take the second derivative test at the other critical point, which is 1/2, right? Then I've got 2 minus 16 times 1/2 is 8, plus 16 times 1/4 is 4, all times e to the minus 4 times 1/2, e to the minus 2, if you will. Well, this is positive, right? E to any number is positive. This is 6 minus 8 is minus 2, that's negative. Negative times positive is negative. If it's negative, that tells you you have a relative max at x equals that critical number. So there's what we're going to do. We're going to find any asymptotes by seeing if there's any point where the limit goes to infinity or minus infinity for a vertical asymptote, or if the limit in the end is x goes to infinity or minus infinity, gives a finite number, we'll get a horizontal asymptote, and then we'll use these tests for critical points to find where the relative minimum and maximum. Finally, we can look for inflection points. Move this over a little bit. By checking the second derivative. At a point where the function is continuous and the second derivative changes sign, we say there's an inflection point. So let's look at the second derivative. It was this one. It can only change sign since this is a continuous function, right? A polynomial is continuous everywhere, an exponential is continuous. The product of continuous functions is continuous, so this is a continuous function. It can only change from positive to negative or negative to positive where it's equal to 0. So we set f double prime equal to 0, and those will be all the possibilities for our inflection points. We have to actually see a change of sign, just not equal to 0 there. But to set the second derivative equal to 0, to look for inflection points, we put 0 equals 2 minus 16x plus 16x squared e to the minus 4x. We can multiply both sides by e to the plus 4x since that's not 0. In fact, let's multiply by 1/2 e to the 4x. The e to the 4x will cancel the e to the minus 4x on the right, and the 0 will still be 0 on the left. The one was multiplied by that. And then the 1/2 will reduce this thing to 1 minus 8x plus 8x squared, all equal to 0. We'll multiply by 1/2 e to the 4x and get that. And where is that equal to 0? Well, this is an ax squared plus bx plus c. So it's x equals minus b plus or minus square root b squared minus 4 times a times c all over 2a AC. All right, so it's 8 plus or minus square root 32 all over 16. Well, 32 is 4 square root 2. So we can divide this through by 4 and call this 2 plus or minus square root 2 all over 4. There it is. At those 2 points, we could get inflection points. We need to see that the second derivative changes sign. Actually, if you think about it, this is a parabola multiplying the exponential. It's going to change sign at these 2 points. Here's 2. Here's 2 minus square root 2. Here's 2 plus square root 2. But let's write it this way. F double prime, as shown here, is twice what we solved here. You pull the leading coefficient out 16 times. X minus the first of these times x minus the second one of these. And the whole thing's multiplied by e to the minus 4x. But that's how you factor a quadratic polynomial. Pull out the coefficient of x squared times x minus the first zero times x minus the second zero. That's exactly how our quadratic polynomial factors. And then the whole thing times e to the minus 4x. That's what f double prime is. You notice that these change sign, plus to minus, at these two respective points. You infer that actually the second derivative changes sign. So this changes sign, plus to minus or minus to plus, at these two candidates, 2 plus or minus square root 2 over 4. So those are inflection points at those x values. Now we've got it, we can plug those in just to see what the function is. There wouldn't be such a bad idea, but it's a little bit of work. What we want to do now is try and sketch this thing. We have a horizontal asymptote, y equals 0, so we sketch that. That was the first time we found. Then we might make a table of some of these important points. Here's x and y equals x squared e to the minus 4x with our function. When x equals, let's do the intercepts first. When x equals 0, you get y equals 0 times e to the minus 4x is 0. So there's an a y-intercept by saying x equals 0. And then you recognize, wait, that's where y is equal to 0. If I put y equals 0, that forces x equal to 0. So it's also the x-intercept. They're the same point. This thing passes through the old origin. That's the only x or y-intercept. If I put y equals 0, that forces this equals 0. Since this can't be 0, x must be 0. And if you put x equals 0 and plug it in, you find out y equals 0. So those are the x and y intercepts. Then we have the asymptote y equals 0. We have the point x equals 0 is also a relative minimum. So we're going to plot this one and we're going to bottom out here. And then at x equals a half is the other spot. Then I get 1/4 e to the minus 2 by putting x equals a half. And we can run that in the calculator. Is about 0.034. All right, so we'll plot here at 1/2 around the maximum of 1/4 e to the minus 2 and say that's about 1/3 of the way to 1. This goes up towards infinity. If you look at the concavity, the second derivative is always positive back here for x less than the smallest of these two numbers. So it's going to be concave up and decreasing through this region. Decreasing because the first derivative is negative. Concave up because f double prime is positive on this piece. Then here, it's still concave up, but the derivative is equal to 0. Here, the derivative is equal to 0, it's concave down. So somewhere in here, well, we found the point 2 minus square root 2. There's an inflection point. Then over here, there's another inflection point. Not for a ways. Out here somewhere. This would be at 2 minus square root 2 over 4. And this will be at 2 plus square root 2 over 4. And then it tends towards this asymptote. So we got a pretty good idea what the graph looks like. We just showed that it's concave up and decreasing through here. I left out some of the details. Has a relative minimum here, has an inflection point here, relative maximum here, then an inflection point here and tends towards this asymptote. So there's the first graph. There's a problem similar to that. Hopefully that looks a little familiar, all those techniques, but now we've applied them to an exponential. What happens is the polynomial multiplies, it makes it wiggle near zero, but out in the end, the exponential dominates, and since the exponential drives up towards infinity here, it just overpowers the polynomial thing, follows the exponential behavior. Also over here, the exponential drives to zero, so you expect it to towards zero on the right. And polynomial just wiggles it near zero. All right. Those are useful things to notice when dealing with exponentials times polynomials, and they give you some simple examples similar to that. Well, here's another one. Well, I took the function f of x equals e to the x over x minus 2. Again, I don't see an even or odd function, so I don't see any symmetries, but I do see I can do some calculus with it. Right? F prime of x, now I have a quotient, so I'll go to the quotient rule. Go to the quotient rule if it's u over v. F prime is v u prime minus u v prime over v squared. So I'm going to do that. X minus 2 times derivative e to the x is e to the x. Minus u is e to the x times v prime is 1 all over x minus 2 squared. There's the derivative. In order to do the calculus concepts again. Inflection points, relative extrema, maybe concavity if we get interested. Well, you want to factor these things when you can. This looks like x minus 2 minus another is x minus 3 times e to the x. All over x minus 2 squared. So there's the derivative. Now you can ask where are the critical points for this one? Well, they're pretty evident once you put it in this factored form. The quotient is going to be 0 after you cancel any common factors, if and only if the numerator is 0. So you need, and e to the x is never equal to 0. So the only place this quotient can be equal to 0 is at x equals 3. That's our only critical point. Again, since it's polynomials and exponentials, they're on any point where the derivative doesn't exist, except where x equals 2. That's not in the domain of the function. So all the critical points, all the points where the derivative is 0 or doesn't exist within the domain, are just x equals 3. Now, once we have that, we can apply the second derivative test or the first derivative test. I think the second derivative test is usually easier for these. I'd like to take the second derivative. Now, I want to take the derivative of this. All right, so I'll take again v u prime minus u v prime over v squared with this u and v. So let's see, v is x minus 2 squared. And then u prime, the derivative at the top by the product rule, is 1 times e to the x plus x minus 3 times derivative of e to the x is e to the x. So derivative of the first times the second plus first times derivative of the second. There's the product rule for this, is u prime. So v u prime minus u v prime, derivative of the bottom. If you write this out, is x squared minus 4x plus 4. You observe its derivative is 2x minus 4. Then it's all over v squared is x minus 2 squared squared. This one's tricky. Maybe the quotient rule and the product rule. Well, this is twice x minus 2, so we get rid of one of these x minus 2's, right? We can say the second derivative is equal to x minus 2 times e to the x minus 3 e to the x plus e to the x is x minus, let's write that as x minus 2 e to the x. Right? And if I cancel an x minus 2 on the top and bottom, then I've got x minus 2 squared times e to the x minus e to the x, x minus 3. You know what, I need to put one more step in here, this is doing too much. So now let's factor x minus 2 out of the top. X minus 2 times x minus 2 I guess I better do this even slower. X minus 2 squared times x minus 2 e to the x is this stuff. And then minus x minus 3 times e to the x times 2x minus 2. Let's factor this slowly over x minus 2 to the 4. There we go. Now we observe there's an x minus 2 here. I can cancel with an x minus 2 here and one of these also. We can write this as x minus 2 squared e to the x minus twice x minus 3 e to the x all over x minus 2 cubed. There it is. Now we can factor out an e to the x and write this as x minus 2 squared minus 2x plus 6 all times e to the x on top over x minus 2 cubed. Now let's see, this is x squared minus 4x plus 4. And then minus 2x makes it x squared minus 6x plus 4 and plus 6 is plus 10. So multiplying all this out, we get that times e to the x. And it's over x minus 2 cubed. Now what are we going to do for the second derivative test? We plug in the one critical point 3, f double prime of 3 is therefore 9 minus 18 plus 10, all times e to the 3 over 1 cubed. 3 minus 2, 1 cubed. So let's see, minus 9 plus 10 is 1. That's positive. E to the 3 is positive. That's positive. The second derivative is greater than 0. It implies you have a relative minimum at x equals 3. The one critical point. How about inflection points? The inflection points will be where the second derivative changes sign. So we'll try setting it to 0. 0 equals f double prime of x is, we found out, x squared minus 6x plus 10 e to the x over x minus 2 cubed. Well, the function isn't defined at x equals 2. And so the only place this is 0 is, again, is where the numerator is 0. E to the x is never equal to 0. So it follows that the only place where the second derivative can be 0 is where this polynomial on top is 0. So we factor that and get, or we use the quadratic formula, x equals minus b plus or minus square root b squared minus 4 times a times c all over 2a is 3, 6 over 2, plus or minus, let's see, this is 36 minus 40. Oh, that's negative, square root of a negative number. What does that mean if I solve that as square root of a negative? That means there's no solution. This is never equal to 0. It's when b squared minus 4ac is less than 0, we call it an irreducible quadratic. It always has one sign. Since it was positive here, it's actually positive for all x. So there's no inflection points because there's no points where the second derivative is equal to 0. Finally, we can get asymptotes. We did those first last time, didn't we? We'll try and take the limit. The limit as x goes to plus or minus infinity. This will also tell us the end behavior. Well, you know, as x goes to infinity, these are both driven to infinity. But L'Hopital's rule says you can take the derivative of the top over the derivative of the bottom, e to the x over 1. Now the top's going infinity, the bottom's going to 1. It follows that the limit is infinity for this one, so the limit for this one is infinity. It goes up to the right, up on the right. No asymptote, but there's still an end behavior that's useful. X goes to minus infinity, now of e to the x over x minus 2. Well, now the bottom tends to minus infinity, and the top tends to 0. Well, 0 over minus infinity is tending to 0. So this one actually says since we have a fixed number here, y equals 0 is approached asymptotically on the left. And on the right, we go to infinity. Over far enough. All right. Now we can try and sketch this one. We want to plot some of the important points. X, Y. And oh, and I forgot the last thing here, the vertical asymptote. Is there any place where the function tends to infinity within its domain? Well, sure it does. As x approaches 2 from the right, e to the x over x minus 2. Well, this goes to positive 0, 0 from the right. This approaches e squared, it's continuous function you can plug in. A finite number over positive 0, this limit is infinity. So it approaches x equals 2 asymptote towards infinity from the right. Now I take the limit as x approaches 2 from the left of e to the x over x minus 2. If x is a little less than 2, we're getting closer and closer. This is smaller. These are negative numbers getting closer and closer to 0. So I'm approaching 0 with negative numbers. This is approaching e squared, a positive number. You just plug it in, it's continuous. A positive number over numbers getting closer and closer to 0 but negative tends to minus infinity. So we approach x equals to an asymptote on the left, but towards minus infinity. Now I know what the graph looks like. So this was a horizontal asymptote here, I should put. This is a vertical asymptote, and this is a vertical asymptote. So I've got a vertical asymptote at x equals 2. I approach infinity on its right. So it goes up like this. I approach minus infinity on the left, so it goes down like that. Then I have one critical point at x equals 3. At x equals 3, I have a relative minimum. Let's see. Oh, and then on the right, yeah, relative minimum. And then the end behavior on the right is to infinity, so it goes like that. With a minimum of 3. Then over here, it doesn't wiggle up and down or anything because there's no more critical points. It can only approach the horizontal asymptote y equals 0. So this time y equals 0 is an asymptote to the left, and there's roughly what the graph looks like. Once we see that, we realize a good idea is to plot a few points, which include this one critical point at x equals 3. We'd like to know what y is. Well, it's y is e to the x. Over x minus 2. So if I put in 3, we get e cubed over 1. E cubed is about oops, 20. So this here is going to occur at about 20. We plot a couple more points, we make this a little nicer. It would be nice to plot an easy point over here. The y-intercept would be nice, right? So you plug in x equals 0 to get the y-intercept, and you get e to the 0 is 1 over 0 minus 2 is minus a half. So this point should look a lot closer to the origin than that one. Deduce that we should make it look more like this. This should be the point, 0 minus a half. Now I've got a pretty good graph, right? A couple more points, I can make it even better, but that's good. So L'Hopital's rule saves the day on these exponential logarithm graphs. Let's try a logarithm now. This was called Newton's law of cooling, actually, is that the rate of change of the temperature in time is proportional to the temperature, let's call it y. Let's say y of t equals the temperature. They use capital T in the section. If you drop a hot body into a cool liquid, it follows this rule, k minus k times y minus some temperature T0, the ambient temperature fluid that you drop it into. So suppose there's so much fluid that the body you drop in doesn't heat it up, it just stays about the same temperature. Then the rate of change of the temperature is proportional to the difference between these two. Newton's law of cooling. As a special case, suppose K is 0.5. And the temperature is 30 degrees. Let's call it T0 is 30 degrees Celsius or something. And well, yeah, all right. And then we get dy dt equals minus 0.5 times y minus 30. Now, and suppose the initial temperature we'll start with a hotter body, is 70 degrees. So this can also apply to dropping a cool body into a hotter. Let's see. No, I'm sorry. This is higher. 70 degrees is the initial temperature. So you drop the 70-degree object into a 30-degree fluid, and what happens? It follows this law with this initial condition. All right. So now you can separate variables, or you can use the linear equations. It doesn't matter. You get dy over y minus 30 equals minus 0.5 dt. Remember this one, separation of variables. Then you can integrate both sides because the variables are separated. On this side, you get ln of y minus 30. And I'll neglect the absolute value because the idea is that the thing is cooling from a temperature higher than 30, so this is always positive. Equals minus 0.5 T plus a constant. Evidently, by solving for y, we get y equals 30 plus e to the minus 0.5 t plus a constant. There's the solution to our differential equation. How about that? Now, from this equation, you can apply the initial condition to determine what c is, right? Apply y of 0 equals 70, because y equals 70 when t equals 0. It's e to the minus 0.5 times 0 plus c. E to the 0 is 1, so c must be 40. So 40 plus 30 is 70. And we have the unique solution for this cooling problem is that the temperature is 30 degrees plus 40. Oops. E to the c is 40, I should have put. Plus 40 e to the minus 0.5 t. Since e to the c is 40. There it is. There's the unique solution. I wonder what that graph looks like for Newton's law of cooling. What does it do? Well, we can apply our graphing technique. Go over to the left end. And there's a problem like this in the section because they're anticipating, even with section 6.4, they're anticipating Newton's law of cooling in chapter 8. What's the sketch? Well, we have an asymptote because the limit as x goes to infinity of this function, 30 plus 40 e to the minus 0.5 t. This is driven to 0, right? E to the minus anything as t goes to infinity. E to a negative tends towards 0 times 40 still tends to 0. So this limit is actually equal to 30. We have a horizontal asymptote, y equals 30. Is there any vertical asymptote? That would be a finite number t that drives this to infinity or minus infinity. There isn't any. All right, you can't make this go to infinity or minus infinity a finite number. But no vertical asymptote. There's a horizontal asymptote and no vertical asymptote. Now we can do our analysis of the relative extrema and the inflection points. Well, we take the first derivative and we say it's 0. Right? Get y equals 30 plus 40 e to the minus 0.5 t. We set the derivative to 0 for a critical point. That's 0 plus 40 times minus 0.5 e to the minus 0.5 t. All right, is minus 20 e to the minus 0.5 t. Well, this isn't equal to 0, and this is not equal to 0. The product can never be equal to 0, so there's none. No critical points. How about that? Maybe there's inflection points. So we take f double prime and set it equal to 0 to see if there's inflection points. Well, that's the derivative of this one. Well, it's just minus 20 times minus 0.5 e to the minus 0.5 t is 10 e to the minus 0.5 t. But again, it's a positive number times a positive number. It's not equal to 0 anywhere. So there's no inflection points. So what do? If I think about it for a second, I start at the initial point when t equals 0, I'm equal to 70 degrees. And I draw my asymptote, which was 30 degrees. Y equals 30. Here's t time, here's y here. And if you look, the second derivative is positive. So it's concave up. The first derivative is negative. So it's decreasing. We just draw decreasing and concave up heading towards this asymptote. Decreasing, concave up, asymptote, y equals 30. There it is. It looks like that. What it is, if you think about it, really, it's a constant 30 plus a decaying exponential, oh yeah, towards y equals 30. That's the graph of Newton's law. Just you start at whatever temperature, 70 degrees, and it decays exponentially towards the ambient temperature in the room. So there's a simple application with a little bit of time we had left there. If I could see how it works for mathematical models. All right, let's try these problems for homework then. They're very similar to what we did, just graphing problems that we sort of skipped over before on exponentials and logarithms. Look at 9, 11, 13, 15, 19, 21, 23. Then over the break, I'm going to put up practice problems for the final. So on Monday, when we come back after the break, we'll go over some of those, and on Wednesday also. Have a nice Thanksgiving.
Sir,
Yeah.
we actually had a question about the recordings for the classes. Are all of those posted on YouTube, or could you post the rest of them?
Oh, the recorded lectures?
Yes.
Oh, if nobody asked for them, I didn't send them. I have
Okay.
today's. That's a good question. If people would have asked more, I would have saved more of them. I don't have very many saved. I'll see what I have of the recent ones. How about?
Okay, thank you.
Actually, I have, yeah, okay. I'll put up what I can do.